charges will be collected on the plates if the dielectric materials is plugging between the plates. What does it mean? we can increase the capacitance using the dielectric materials. That's the reason. Okay. However, any dielectric materials has some parameter which is connected with the capacitance. Its name is permittivity. So we've got the permittivity of air. Yeah, it is the constant value. However, in Europe, we said that this is the permittivity of the vacuum. In fact, in the English book, they call them like the permittivity of air. Yeah. This is the some reference permittivity for us. Yeah, this is it with the zero here and the notation. Okay, what is the relative permittivity? This is the ER. This is the permittivity of the material of the dielectric, and this relative permittivity, it is equal permittivity over the permittivity of air. Yeah, according to the reference. So if we are taking into account two capacitors, one of them it is the capacitor with air gap and with some dielectric materials, which has the relative permittivity, we'll see that the differences in capacitance, as you see, will be ER higher than the capacitance when we have these dielectric materials between the plates. That's why the capacitors, if we wanted to produce the capacitor with the huge capacitance, we wanted to find the materials, the dielectric materials, which has the very, very huge relative permittivity to get, in fact, the higher capacitance. Okay. What the next thing about the capacitors? Of course, we have to know that this is not true that the capacitor, it is just the capacitance. No, it's not true. Why? Because you have to know that any materials, anyone, have some resistances. Even if we consider the electric materials, and also they have some resistances. Of course, they are so huge, for example, lots of mega ohms. However, they exist. And that's why if we wanted to consider the equivalent model of the capacitor, in fact, it is consists of the pure capacitance. Yeah, that's true. And this is the parallel connections with the RL, where the RL, it is the resistance of the dielectric materials, which is put it between the plates. So as you see, we can observe something like that, like the liquid current. What is the liquid current? This is the what is the liquid current? Okay, let's imagine that we have the ideal capacitor. We plug in it to the voltage source. We collect some charges on it. So we've got some voltage drop between the plates. If this capacitor will be taken off from the electronic circuits and we take it to the hands, so we'll have the voltage drop between the terminal of the real of the capacitor. For example, I don't know, 1 volt. Yeah, and if it is ideal capacitor, this 1 volt will still remain the same to infinity in time. Yeah. However, if we have some resistances of the dielectric materials, so in fact we'll have the voltage drop between the terminals. However, by this internal huge resistances, very slowly the current will be passing through from the top to bottom plate, but it will be passing through by the material, by the dielectric, due to the huge RL. What does it mean? The potentials between the plates will be reduced and reduced in the time domain. That's why we can say that we've got the discharging process of the capacitor. Yeah? So any capacitor, real capacitor, in fact, after time they lose the charge which was collected before. Okay, the next thing you have to know that the real capacitor has some temperature effects. In fact, its capacitance depends on temperature, and it is the same story like for the resistances. This temperature coefficient is put it using by the ppm way. So we've got the ppm over the Celsius degree. Yeah. So how we can calculate it? Very simple. If we have the capacitor which has the temperature coefficient equal, for example, 150 ppms per Celsius degree, and you have, for example, the capacitor with nominal value equal 100 microfarads, so we can calculate what will be the change, what will be the changes of the capacitance by the any one Celsius degree changed. So it is the 150 over the 1 ppm. 1 ppm is 1 million, yeah, multiplied by nominal value. So we've got, as you see, 15 nanofarads per Celsius degree. What is the characteristic of the temperature dependent of the capacitance? It depends of type of materials, of the dielectric materials. For example, for the Z5U ceramic, which is typically used, however, in fact, we've got another one. The changing of the capacitance according to temperature looks like that. So as you see, the best value, the higher capacitance we've got for the around the room temperature. If the temperature are going up, the capacitance are decreased. Also, where we can observe that capacitor is working at the very low temperature, also the capacitance are reduced. It is very important in advanced electronics systems. You have to very often consider the temperature environment conditions where the capacitance or not the capacitor but your electronic circuits, which is considered capacitor, will work. It is very important. Okay, very quickly, of course we've got a lot of capacitors. The typical value is put it here. In fact, it doesn't matter at this moment. Yeah. We've got the different type of the electric materials. This is the polystyrene foil films, polypropylene. We've got or ceramics. We've got a lot of components, a lot of materials using.
Can I ask something?
Yeah.
Why with resistors we have symmetric tolerance, for example, plus minus 5%, and with capacitors we have, for example, 5% plus 5% minus 20%?
Yeah, because the materials here as the dielectrics, this is not the pure material. For example, this is the structure of the different or the others doping materials. In fact, so as you see, the characteristics, in fact, it will be not linear, for example, but they change. It depends on temperature. What the atoms for the different dopings or different materials are, what the values, what the properties they have in the different temperature. So that's why it is very hard, in fact, to say. In fact, why it is not linear? Why? Because it is the complex of the different materials. The structure of the materials are very difficult, in fact, according to the chemical point of view. So that's why this is not like the resistances. We've got some I don't know, carbon layer, and we know what happened. Yeah, this is almost linear. Yeah. In this case, the structures are so different from chemical point of view, physical point of view. That's why we can observe the changes of the parameters or performance of the not the performance but properties of the materials are different, completely different. It's not linear according to the temperature changes. That's the reason. Okay. Hello. Okay. So the next step. Well, the transient analysis, if we have the capacitor in our network, it is very important for you also. We have the two phase if we consider the capacitor in the electronic circuits. We have the charging phase and discharging phase. If we are take it the pure the capacitor, for example, which is empty at the first moment, and we build some RC network, and we plug in the voltage drop and the switch, we have to know what happened if we at the moment when we turn on the switch. Yeah, this is very important. So okay, if we turn on the switch, we'll have the current flow IC in our electronics. However, you know at this moment, this is not the typical current flow, because here we've got the electric material. It is not possible that the simple that the current is passing through the electric material. Yeah. So the current here I see at the first moment when the switch is turned on is connected with the moving of electrons between the plates. Yeah. What was what I talked previously. So how it looks like, the voltage drop on the capacitor VC during the time when, or starting from the moment when the switch was turned on. The shape or characteristic looks like that. It's put it here on the right side picture. It looks like that. It's going from 0 to the maximum value. Why? Why we've got that situation? Why? Because when we turn on the switch, in fact, the capacitor is empty. So they haven't any charges on the plates. The charges appear due to current flow, so electrons movement from the top to the bottom plate. But at the first moment, voltage drop on it was equal 0 because we haven't any charge. So when the time is going by, we can observe that the charges on the bottoms are increasing. So that's why the voltage drop on the capacitor are also decreased. Yeah. And that decreasing to moment when, of course, the voltage drop on this capacitor will be the same like the value of the voltage source. We know from the Kirchhoff voltage law that there is not, in this moment, it is not possible to get the higher voltage in our closed loop than which is given by the voltage source. Okay, so as you see, we'll collect the charges on the plates, the voltages is increased, and then they get the maximum value equal E. The mathematical function of this charging phase, or charging process, is given by the exponential function e to minus x. Okay, so you have to know typically the mathematical expression for e to minus looks like that. Okay, and 1 minus e to minus x is given that. Okay. Okay. What the next question is? What is the time constants here? Tau. You have to know that the time constants equal tau. It is the time value when the charging process or the mathematical function of connected with the e to minus x get the around 2/3 of the maximum value, or for the expression like the e to minus x, they have the value of equal around 1/3 of the maximum one. So that's the time when these two values can be reached during the charge or discharging process. Okay, so if we're coming back to the charging phase, the capacitor, it is given by that formula. This formula is given by that equation, minus 1 minus e to x. In our case, it is x, it is t over tau. T, it is a time. The tau, it is time constants. Everything we have to multiply by e. Why? Because this is the maximum value what is possible to get. Yeah, it is e. Okay, great. So the next thing, so this is the expression for VC, looks like that. 1 tau, it is the place where this function reach the around 2/3 of the maximum value. So it is around 63.2% of the maximum one. This, it means that is the 1 tau. This is the 1 tau, which means it is the time constants. Time constants, it is equal R multiplied by C. And as you see, if we consider the units here, as you see, in fact, we'll get the seconds as the unit of the tau. Very interesting. Okay, what about the moment when we can the voltage drop on the capacitor reach the maximum value? Of course, we can say that this is the exponential function here. So in fact, it is going to infinity. Yeah, to get the maximum value. So in electronics, we have to choose some time when we can say that we've got the steady state, which means that we've got the maximum voltage drop on the capacitor in this case. So in electronics, this time was chosen like the 5 times tau. Which means we've got, in fact, the voltage drop on the capacitor equal almost 100%. This is the 99.3%. So we can say that if we can say in that form that the steady state for the electronic circuits where we have the capacitors is or can be reached after time equal 5 tau. The tau depends on the resistances and the capacitance in this case. Okay. So this is very simple calculations. Yeah, what happened if we take it 5 tau times, and that's why, as you see, we get the almost 99.3% of the maximum E. This is the very important thing. However, I think it's very simple. What happened with the current, which is observed in the closed loop? Yeah, in this case, how it looks like. Okay, it's opposite to the voltage function. Why? Because at the first moment when the capacitor was empty, yeah, we can say that every electrons from the top side wanted to go to the bottom one very quickly. But as you see, we've got the resistor here. So this resistor are limiting the value of the current which is passing through here. So that's why we can say that at the first moment, the current when the switch is turned on has the maximum value, but it is limited by this resistor. Because the capacitor at the first moment is empty, so there is no charge between the plates, so the voltage drop on it is equal to 0. So we can say, according to the Ohm law, if the voltage drop is equal to 0, we can say that it is like this short circuit. Yeah. So the current, the maximum current IC at the first moment when the switch is turned on, it is limited by the resistor. So it is equal E over R, according to the Ohm law. That's why here the maximum current at the moment equals at the time equals 0 when the switch is turned on is limited to the E over R. And then they are going down. Why? Because the charges is collected on the plates, and after 5 tau, we'll have the situation that the current IC is going to 0. Why? It is simple. Because we have the same voltage drop on the capacitor and the voltage source. So the potentials between these 2 points are the same. So the current is stopped flowing, in fact. Okay. So that looks like the expression for the transient analysis where we have the RC network. So one thing, I thought about it. I have thought about it previously. At the moment, in fact, if we consider the electronic circuits with the capacitor and wanted to make the transient analysis according to the charging phase, in fact, and the switch is turned on, we can say that the first moment with the capacitor, empty capacitor, it is important, empty capacitor, looks like the short circuit. Only at the first moment when the switch is closed. Yeah. And after time equal 5 tau, so you can say that it is for us, it is the steady state, the current IC is stopped flowing. Yeah. So we can say then that the VC is equal E. So the capacitor, it is in fact looks like the open circuit in this moment for the steady state, because the current is flowing and we have got the same voltage drop on these two components. Also, there is no voltage drop on the resistors because we've got the same potential here and here. Okay, how it looks like the voltage drop on these resistances R is given by this formula. It is the E multiplied by E to minus T over tau. That's the changes of VR. Great. What else? Yeah, this is just the expression for the voltage drop on the resistances during the charging phase. As you see, yeah, it's going from the maximum one, yeah, when we have the short circuit. So as you see, the VR is equal to E. You've got the short circuit, and when the time is going by, then the current IC are stopped flowing. So the VR is going to 0. Yeah, the potential are the same. So after 5 time, we can say that we've got the 0 volts between the 0 volts on the R resistances. Great. I'm just wanted to take a look at the time. Okay. I think. What are you thinking about that? We should maybe make some break.
Yeah. Okay. Can be.
Yeah, that's right. You agree with it?
Yep.
Yes.
Okay, so when we can coming back, maybe what? The 11:15?
Sounds
Okay.
good. Okay.
Sure.
Yeah. Okay. So I think I'm not end the I not wanted to ending the meeting at this moment. Okay. So I'm just leave it at like it looks like at this moment. Yeah. Okay. Yeah. The Zoom software. Okay.
Okay. Okay.
Fine.
I'm not closing the meeting at this moment. Okay. So we'll see. We'll see at the 11:15, and we'll continue it.
Sure.
Okay. So see you.
I should book the tickets to India now. Oh, first go. Most
Hello, do you hear me? Hear me?
Yes, I can hear you.
Yeah.
What's up?
I'm just chilling.
In dust? Yeah, chilling in dust.
Corona time!
Can I mute him? I cannot.
Wojtek, I love you.
Yeah, Wojtek is a fucking legend.
I love you all too.
Go somewhere else, go somewhere else.
I need to
I want
come
world
up with
tour.
something. Let's see.
Okay, let me see who's in the room. Where's our teacher?
On the break.
The sub break.
Ah,
Wojtek, is that a green screen behind you?
No, you don't need a green screen. You can just click, like next to the stop video button, there is this arrow. You can click it and just choose virtual background, and it works without a green screen.
Where are you guys? Why this hall is empty?
Wywąsisko, to jest po prostu chłop, który ewidentnie powinien streamować.
Słyszę kogoś. I hear someone but really quiet.
what made you change your style, Wojtek?
I wanted to shorten my beard a little bit, but I did it. I accidentally did too much, and then I just decided to shave it all. And then I thought it would be funny to leave the mustache because it's gonna look stupid, and it does. But I'm not going out or anything because of the quarantine, so why not?
You look
Yeah,
a
but I'm
bit
growing
like
the
Captain
beard back.
Disrespect.
Yeah, I like this style.
Thanks.
It's very troll, you know.
You can always trim it a little bit on the side, so you have just a small patch under your nose.
Lol.
Yeah, there's a problem that like the middle doesn't grow for me, so I cannot embrace my inner
German.
Austrian artist.
Austrian artist. Fuck.
All we have left is Austrian artist.
If only he was better at painting.
Igor, which building are you in?
C16, of course.
You're muted.
He's muted,
What?
but the mic doesn't work.
Oh, what? Maybe now?
Yeah. He said guess this.
I recognize that couch.
What?
Having an
Oh.
interview?
Yes, I'm gonna have a new job.
Okay. Time to ghost.
Oh, he's in space.
So, what kind of job do you have?
I'd rather not mention it.
How did they let you in?
By the magic of computer science.
Whoa.
And virtual backgrounds. Yeah, but I was there 2 days ago.
Which is like the Big Brother show, I think.
I wanna go home.
Who wants to go home?
Hardik.
Adric?
Yeah, I want to go home. I want to go India.
Really?
Yeah.
You don't like the Poland?
No, it's not a problem. Like the virus is spreading, and I don't want to die in Poland.
Yeah, in fact, we can laughing about. In fact, we got a lot of problems, I think, and we'll have more. I
We
suppose.
have around more than 300 cases now.
That's right. That's right. So I think at this moment you can live in the Poland, yeah, or not?
Yeah, probably, but we are trying to contact embassies and to asking us to evacuate the students because all of the students are in Polytechnic are trying for this. Yeah.
Okay.
My dad told me 1 week ago, just come back to India, and I was a stupid, dude. I'm not coming back.
You know, maybe not as stupid, but I think maybe he has right a little bit, yeah, because I know that it is better to be at home for that situations. I know it.
That depends, because if you have older people at home, or
Yeah, that's
something,
right. Yeah,
it'd be better to
stay.
away.
I think. Yeah.
Probably, maybe after 30, if the virus gets more spread in after 31st, in the embassies told us that Indian army planes will be come to evacuate us. So we have to be ready all the time.
If you're like this scared, I would just sit at home if I were you, because going there will be much more risky.
I'm ready to take the risk. I'm ready to take this risk.
But why do you want to go there?
Putting other people at risk more than you.
What?
If something happened to me, I don't want to die here.
Don't worry, you are so young.
Yeah, I would be more worried about like coming back to my parents, because if we get sick, it's not that much of a problem. But
and if he goes to India, you'll just like take planes, go with people and stuff. So.
Yeah, that's right.
But if the government evacuates, then they will be like putting him under quarantine and stuff for 14 days.
Yeah, for 14 days. If I went to India, it will be take 14 days. Some army place, I will stay there.
I don't want to risk going back. So like if something happens, the school starts, I'm just there stuck.
My friend went to India he went to the Germany and then he take the flight to India. I was like, I can do the same.
yeah, I mean, I even avoid like public transport right now. So.
Yeah.
No, in morning we get some new mail from embassies that don't travel to any place till we get you any information about this evacuation. To stay where you are.
Okay, guys. So I think it is time to start up. Can we start or not? What do you think?
Yes, okay.
Yes. Yeah. Okay. Yes, let's do it. Maybe. Okay, so let's coming back to electronics.
Mute yourself. Can I ask one question?
Yes.
Is there a way to convert farads to, for example, watt hours?
You know, I don't hear you very good. I think there's some maybe problems with the phones or not.
Maybe he should try to write it in chat.
Probably farads to watt hours.
The energy stored in the capacitor into actual work force energy. Can we convert it?
Okay, could you repeat? Aha, you are using the chat at this moment.
Yeah, because I said I'm sorry. I said to him to write the question in the chat because we can't hear him.
Okay.
And he's asking if we can convert between the energy in the capacitors, like from the capacitance in farads to watt hours, for example.
Okay. Sorry, I'm just reading the chat at this moment. How many? Aha, is in 1 farad. We can at this moment consider the watt hours according to the farad. How? We are going to the for the few slides we'll have the what is the power, what is the dependence in the power connected with the capacitance. However, you should know that there's no dissipation power for the capacitance. In fact, this is only the storage power. And I will give you some equations for it. Okay, can we start?
Yep.
Yep. Okay. Okay. So now we are going. Let's go to the discharging process, which can be considered for the capacitors. Okay. We know what happens